reached. Reverse osmosis is when the opposite occurs. By pressurizing the concentrated solution, the seawater, we are able to force water molecules to pass from the salty seawater solution through the membrane to the fresh water.
The St. Mary's Water Recycling Plant uses reverse osmosis to further treat wastewater after the ultrafiltration process. Reverse osmosis membranes are constructed from a membrane flat sheet. It is comprised of 3 layers: a polyester fabric support base, a microporous polysulfone layer, and a 0.2 micron thick polyamide barrier layer. The polysulfone layer strengthens the very thin barrier layer. It is the barrier layer that removes nutrients, chemicals, bacteria, and viruses from the water. The membrane flat sheet is combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets for the feed water. A sheet of permeate spacer is added to the membrane sheets and feed channel spacer. This enables the final recycled water product, or permeate, to flow evenly across the entire membrane surface, even under high pressure. The back of the membrane is completely sealed to the edges of the permeate spacer. The membrane sheets are glued along each of the 3 exposed sides and rolled around the core tube. Feed water is forced through the feed channel spacer and into the barrier layer of the membrane. Water passes through the membrane surface into the permeate channel. It flows in a spiral direction and collects in the core tube. This water is the final recycled water product, or permeate. There are 7 spiral wound elements loaded in one pressure vessel. Once the end adapter is connected to the last element and the pressure vessel is sealed, feed water can be introduced. Feed water is pumped at high pressure into the vessel. As it travels, small molecules like water pass through the membrane, while larger particles such as salt, bacteria, and viruses do not. The final recycled water product is collected from the end of the elements. The concentrate or reject from that vessel flows to another stage, producing more recycled water. At St. Mary's, there are 6 reverse osmosis treatment trains, each with 3 stages. This design produces the highest amount of recycled water with reduced concentrate waste. Stage 1 has 52 pressure vessels, Stage 2 has 24 pressure vessels, and Stage 3 has 12 pressure vessels. 58 million litres of feed water enters the reverse osmosis system on a daily basis. As the feed water passes through each stage, more recycled water is extracted. 65% of recycled water is extracted at Stage 1. The remaining 35% is passed through Stage 2, where a further 10% is extracted. The final 25% is passed through Stage 3, where the last 5% of recycled water is extracted. 80% of all feed water is recovered as recycled water. An average of 50 million litres of recycled water is produced every day at St. Mary's. The remaining concentrate contains so much salt and impurities that to recycle it would not make economic sense. This concentrate stream of 8 million litres a day is sent to North Head Wastewater Treatment Plant, where it is treated and released into the ocean.
Batteries is used. They are maintenance-free and suitable for warm tropical climates. Before shutting down at night and during longer standstills, the membranes are automatically flushed with fresh water to avoid frequent replacement. The solution comes as a hybrid, so it's possible to double the water production at night by grid or a generator. The units are ideal for remote applications as they are compact, plug and play, and easy to operate. They can be delivered in a small container ready to be put in operation. Maintenance is limited through automation and the use of highly durable components. The water quality is constantly observed and remote monitoring and control is included for stress-free operation. Coastal communities, properties, resorts, municipalities, and industries can now get access to affordable, clean water for generations to come. Benefit from unlimited resources today and contact us for a free feasibility assessment. Join us in solving freshwater scarcity using only the sea, sun, earth, and wind.
To protect the reverse osmosis membranes from becoming clogged by solid particles that can be suspended in the seawater is filtered before passing through the membranes. This is accomplished by using multimedia filters, which are tanks or vessels containing a series of layered granular materials. These materials can be anthracite, garnet, sand, pebbles, and/or gravel, which are assembled in layers. The filters remove sand, twigs, seaweed, and other particles from the seawater. In some cases, other types of membranes, known as ultrafiltration and microfiltration membranes, are used instead of multimedia filters to pre-treat the seawater. Next, the filtered seawater travels to the cartridge filters, which act as a second stage of filtration. Cartridge filters used for seawater reverse osmosis are typically made from a yarn-like synthetic material that is wound into cartridges. These remove even smaller solid particles from the seawater, such as fine sand and clay, before the seawater proceeds to the reverse osmosis membranes. High pressure pumps increase the pressure of the seawater up to 1,000 psi. The pressure needs to be sufficiently high to overcome the naturally occurring osmotic pressure and force water from the saltwater side through the reverse osmosis membranes to the freshwater side. The salt particles in the seawater are rejected from passing through the membrane to the freshwater side and remain behind on the concentrated saltwater side. The reverse osmosis membrane can be thought of as a number of sealed envelopes connected at their open ends to a tube. There are spacers between each envelope which allow water to flow across the membranes. The membrane envelopes and spacers are then wound around the tube like a roll of paper towels. The reverse osmosis membranes are then enclosed in a fiberglass shell. The membranes are connected end to end, usually 6 to 7 membranes together, and housed in vessels that are built to withstand pressures up to 1,200 psi. As the pressurized seawater enters the pressure vessel and flows across the membrane surface, the water molecules are forced into and through the membrane envelopes, leaving the salt molecules behind. The desalted water passes through the membrane and emerges at low pressure, where it is collected in a tube and directed to one end of the pressure vessel. The concentrated salt stream that is rejected from flowing through the membrane continues to pass across the membrane surface, where it is collected separately. The concentrated salt stream retains about 55% of the total energy of the seawater stream that was originally fed to the membranes. To reduce the energy that is required to operate the reverse osmosis plant, the pressurized concentrated stream is piped into an energy recovery device. Here, up to 98% of the energy of the concentrated salt stream is transferred to an equal volume of the incoming seawater in an isobaric energy recovery device. The energy recovery device significantly reduces the plant's operating costs by recovering the concentrated salt stream energy and using it to pressurize 60% of the seawater that is fed to the membranes. The concentrated salt stream will have about a 60% higher salinity than the incoming seawater. The concentrated salt stream is sent back to the ocean through a brine disposal well, or a device known as a brine outfall. The brine outfall is situated in an area of significant ocean flow so that the salt levels are quickly returned to equilibrium with the ocean. The location for the outfall should contain no sensitive marine ecosystems. In a properly designed brine outfall, no noticeable increase in salinity can be detected at a distance of a few meters from the discharge. The pressurized seawater leaving the energy recovery device has its pressure boosted by a small booster pump so that it is at the same pressure as the seawater leaving the high-pressure pump. The boost is necessary as some pressure has been lost as the stream travels through the reverse osmosis system. Approximately 40% of the seawater that enters the system is converted to potable water during the reverse osmosis process. The potable water is further treated by adding calcium carbonate to improve the taste and bring the pH to the neutral range. Chlorine is also injected to provide disinfection properties as the water travels from the reverse osmosis plant through the distribution pipes to homes and businesses. When proper conservation of natural water resources is practiced, water reuse has been applied, and a water deficit still remains. Seawater reverse osmosis can offer a sustainable alternative. With good stewardship, it can provide life-sustaining water for coastal communities. Desalted water supplies, which are not susceptible to drought and other natural disasters, can provide a clean, safe potable water supply.